Okay. So we're going to learn how to formulate state equations for systems that have two-port elements in them. We learned how to draw linear graphs for them last time, but we didn't learn how to find a normal tree. That process is a little bit different, and then find the state equations. So we'll go through that today. And it's like super loud, isn't it? It's crazy. All right, we'll get through. Maybe we'll pump some jams of our own if it gets too crazy. Maybe some Taylor Swift or something. All right, so the first step is to draw a normal tree if you're going to formulate state equations, because it's from the normal tree that we know which of the continuity and compatibility equations to write. So, in order to draw the normal tree, the process is very similar to what it was before, but a couple of our rules have changed. A couple of our steps have changed. So, the first step is the same, draw the system graph nodes. So we did that before. Remember, we kind of often skip that because we know the only reason to really draw the nodes is to remember that you have to connect to every node in the graph if you're going to have a full normal tree. So that's a good check on yourself. Step 2 is to select tree branches using the following rules. Rule A, no loops can be created. So we've done that before. N-1 branches must be selected. N is the number of nodes, so we also had that before. One and only one of a given transformer's two branches may be selected. So that's new, right? That's a new rule. So transformer, if you have a transformer in there, then one and only one of the two branches of a transformer may be selected. And finally, D, both or neither of a given gyrator's branches may be selected. So it's transformer, one or the other needs to be in the normal tree. If it's a gyrator, either both have to be in or neither. Okay? Now, those are the rules that we have to follow. Remember, there were two rules before. It was the first two. So we've added two more rules on. And then step 3 is to select tree branches in the following order until no more can be added without breaking a rule. Okay? So, A, select all across variable sources to be in the normal tree, which is exact same first step that we had before, right? Nothing changed. As many as possible A-type energy storage elements. Once again, same exact step as before. The third step is where things change a little bit. And there is some subtlety to this step, okay? For small graphs, it's not too bad to deal with the subtlety, but for a large graph, it could be more complicated. So we'll typically in this class be concerned with small graphs, but just so that you're aware, for a large graph, you might have some struggles with this. So C, select the correct transducer branches, minimizing the number of T-types in the tree. This is the subtlety that makes it hard. So transducer branches are going to be either transformer branches or gyrator branches. So either we need to select one of the two transformer branches. We need to select either both or neither of the gyrator's branches. And the caveat is where it's a little bit tough. The caveat is that we have to minimize the number of T-types in the tree. We haven't selected T-types yet. They're the lowest priority to get into the tree. And usually we don't put any in the tree, right? So notice that this step sort of refers to the last step. So what you kind of have to do is select each one. So try each possibility and finish the steps and see how many t-types you ended up with. And you want to minimize the number of t-types in the normal tree. So either you can have some nice insight into where it's going, or you can just try all the possibilities. Usually, so if you have a graph with only one transducer element in it, I think that the most that I do in this class is maybe 2 transducer elements in one problem. If you have one in a graph, you have 2 possibilities, right? You have to select either, if it's a transformer, you have to select either the left one or the right one. And so you have 2 possibilities. You have to try it with the left one and try it with the right one. If you have a gyrator, you have to either select both or neither, so you have 2 possibilities there too. But if you have 2 transducer elements in your tree, then you have 4 possibilities, right? Mm-hmm. If you have 3 transducer elements, how many possibilities do you have?
That'd be 6.
6? 8.
Oh, yes.
Because so
Because that has 4 times.
2 raised to the power of however many you have.
Okay.
So it gets pretty big pretty quick, the number of possibilities. It grows exponentially. So if you have a really large system that you're modeling, you do have to be careful with this. Not that you can get around it, you still have to deal with it somehow. You may or may not be able to deal with it by making an argument that doesn't require you to select all of them. You might be able to say, given the topology of the graph, the connections are such that choosing these elements are always going to minimize the t-types. That's possible to do. Or you can do a brute force thing where you just calculate it for everyone. Yeah?
Generally, wouldn't you want to look for transducer branches that share a node with the t-type element?
So, yes. That is a good guideline to use. It's not necessarily always going to hold true,
Okay.
but if you choose one that connects to a t-type element to be in the normal tree, then you have reduced the likelihood that you'll need that t-type to be in the normal tree to finish the tree. So that's a good way of helping guide you through it. But it's not. I don't know that can be generally applied. I would have to see a proof of that. I haven't seen that. So, but maybe it'd be interesting to explore. Okay, so now that we've learned how to deal with the transducers, we move on to our next priority, which is D-types, and then finally T-types. So notice that this is sort of iterative. Potentially you have to go through this part a couple times. But usually there's only 2 possibilities, and for simple systems that we're going to do in this class, so you can just look at it and say, okay, if I choose this one, then this t-type is in it. If I choose this other one, t-type's not in it, so therefore I'll choose this branch. And it usually just takes a second to do that. But you just have to be cautious as you apply that rule. So there's only one new rule in there. We just interpolated it between this rule, the A-types and the D-types, right? Transducers were after the A-types. All right. So state equation formulation. Is it going to be all new way of doing things? No, thank God. We're just going to do the same exact process. So same method as before, with the following alteration. 2 elemental equations for each transducer will be found with the appropriate transformer or gyrator vector equation. So we remember in the last set of notes, we developed the 2 elemental equations for a transformer and the 2 elemental equations for a gyrator, right? And then we found out that the transformer ratio and the gyrator modulus just depends on the system that you're using. If it's a motor, it's a certain transformer ratio. If it's a lever, it's a certain transformer ratio. If it's a gear, it's a certain transformer ratio. if it's a piston cylinder, it's a gyrator. So there's a certain gyrator modulus for a piston cylinder. It has to do with the area of the cylinder or the piston. So, okay. So let's do an example. An electrical transformer is a device that can transmit electrical power between two electrically isolated circuits through electromagnetic coils. And so we use this sort of symbol. These are highly efficient and used ubiquitously in power transmission to step up or down voltage and to electrically isolate circuits. Power is approximately conserved in them, so our usual relationship here that if you add up all the power in, then it must equal 0. The equation that characterizes the relationship between these variables then is this. In other words, it's a transformer. Probably not surprised that it's a transformer because we call it a transformer, right? But it's a transformer in the sense that we're talking about transformers. So that's why whenever I talk about an electrical transformer, I try to say electrical transformer, but sometimes I will forget to. So sometimes you just have to be able to tell from context what is being talked about. All right. So and the transformer ratio is 1 over n, where n is equal to the ratio of n2 over n1, where n1 and n2 are the number of turns in each coil. So that's the theoretical transformer ratio. Of course, you could also come up with an experimental value as well for a given transformer. You could measure the voltage and current being supplied, and then you could measure the voltage and current being absorbed on the other side, and you would be able to determine what the transformer ratio is. So we have, fortunately, electronic components, if you're given a transformer ratio, they're pretty good. Like just the theoretical one is pretty good. The actual one as built, of course, will be a little bit different, but usually they're close enough. But you guys have experienced this in lab already. Resistor values, they're not exactly what they're supposed to be. Like nothing is exactly what it's supposed to be. And there are different degrees of sort of variance there. So, next example is to actually write the state equations for a transformer. Now, let's see. Do I have time? Yeah, I have time. Okay. I'm reading this book right now. This has nothing to do with the lecture. I just thought of it. Okay. So, I'm reading this book right now called Logicomics. Has anybody read this book?
Sounds interesting.
Oh, it's so great. It's so great. It is a graphic novel. It's like 300-page graphic novel that is mostly about Bertrand Russell's life. Okay? So Bertrand Russell was a very famous logician, mathematician, and philosopher, and in the 20th century. So like he was very influential. Well, late 19th century. So it was like around 1900. He was like in college, I think, or something, and then I don't remember when he died. I think he died in like 50s or 60s or something. But anyways, really brilliant guy. I actually don't love his philosophy that much, but this book is really cool because it's introducing you to all of these different characters from that time, which is really interesting. Like all of the like really famous mathematicians, and like Cantor, the guy who invented set theory, shows up in it. And it shows us really interesting. It's a story. It's a story about like his life and all these people, and it sort of weaves you through all of these different characters that invented set theory and then invented all of the math that we use now, or most of it. and it's really, really cool. So they talk about the ideas too, but it's a graphic novel, so it's pretty digestible. Like I've read half of it in like 2 sittings. Like it's not hard to read. It's pretty easy to read. Anyways, I thought I would tell you that because if you're looking for things to buy yourself for Christmas, it's just a suggestion. So something to think about. All right. So on with the chlorophyll. All right. So.
The Dr. Rico Honey Book Club.
Yeah. I did do a reading group when I was living in the res halls here. I actually did. I started the Society for People Who Read. No goats allowed. That was one of the rules. It was like the only rule. No goats allowed.
An acronym or just?
No, just goats.
Okay.
We just don't like them.
Just goats can read.
But like we would just get together and read silently.
How many people?
Like 10 people would come.
Okay, so it wasn't like just 3 people randomly reading in a room.
No, I mean sometimes it was. This was inspired by. There's this thing that happens in Seattle. I forget which hotel it is, but there's a hotel downtown, and once a month, it's like the first Tuesday of each month or something. People start showing up. There's nobody in charge of this. People start showing up, and they take a seat somewhere, like the lounge area. There's like this big dining area or something, and people bring a book. They open their book and they start reading. And it's like there are tons of people there silently reading together, and it just happens.
There's a
The same book?
romantic comedy in there.
Yeah.
It's
Or any
any book.
book, no?
Just bring and then just read silently together. It's like it's really weird, but it's super cool. Anyway, so it's inspired by that. So
That's
I don't know. I don't do it though anymore because it was in the res halls, and I don't really go hang out there now because I don't live there anymore. It would be weird. So I stay away from the res halls. It was less weird when I lived there, but it was still slightly weird, and then now it's just weird. So, all right,
convention.
sign convention. You guys actually don't even realize how good I've been this year about not going off on tangents like that. I love doing that. It's so fun. Okay. Derive a state equation for this circuit. This circuit's pretty basic, right? Voltage source, got a couple resistors here and a capacitor, so not a lot going on in it. But then we got this transformer in there, which we learned to deal with back a while ago because we learned how to deal with writing 2 equations for it. But we didn't. We haven't learned how to deal with it with state equation formulation. So now we're hopefully going to apply our rules that we've learned and find the state equation for it. So I show the linear graph and normal tree. Well, let's walk through that. So draw the linear graph. That's pretty easy to do for this circuit, right? Draw the linear graph. For any circuit, it's pretty straightforward. So we draw the linear graph. And then we go through our rules. So cross variable sources. So we select the voltage source. A-type energy storage elements. So we select what? The capacitor. Okay. Then we've got the new rule, right? We have to select either, so it's a transformer, so we have to select one or the other side, right? Minimizing the number of t-types in the normal tree. How many t-types do we have in this linear graph? None. So doesn't matter. We can choose either one. And actually, you have a choice here. You could choose this one, or you could choose this one. The state equation that you'll get will be identical. It doesn't matter. So I chose side 1 to be in the normal tree, which left side 2 out. And I can't select anything else besides the next step would be Detypes. So one of the resistors I can select to be in the normal tree, but I can't select the other one or create a loop. and we have a complete normal tree now. Okay, cool. All right, good. So let's do variables in system order. What are the primary variables? VS,
V1,
V1,
VR2,
VR2,
VC, and then IR1,
IR1.
and I2.
Yeah. So secondary, we just transpose those. IR2, IC, V, VR1.
Minus half.
Sorry?
Minus half of y. You wrote IR1 twice. Minus half.
But I deleted it.
I deleted it.
You still gonna mark me down, man? So harsh. Fortunately, I'm not that harsh on you guys.
Yes, you are.
I disagree.
Maybe just for you.
Oh man, it's getting you back. An eye for an eye is my motto. Okay.
Give him 10 points because he caught his mistake.
State variables. Okay, which of those primary variables are state variables?
No, wait, it would
So-
be R or 1, so it has to be VC.
So we have to find the A types that are in the normal tree and the T types not in the normal tree. There are no T types in this graph, so we don't have those. A types in the normal tree. There's only one A type, and it's in the normal tree. So it's the across variable because it's in the normal tree and VC. So it's first order system, right? N equals 1. Super easy. You guys are probably really disappointed it's not higher order than that.
Yeah.
So disappointed.
Yeah. Okay. So the elemental equations. We're gonna use. So we're just gonna define what TF is. So TF is a transformer ratio. We know it's a transformer. We already went through that discussion. We know that its transformer ratio is 1 over n. Okay, and here I wrote 100 and 500 over here. So what that means is that n1 is equal to 100 and n2 is equal to 50. So n is n2 over n1, right? Which is 1/2, right? 50 over 100. So n, so first I'll write n equals 50 over 100 equals 1/2. And then we'll separate that from TF is equal to 1 over n. So what is TF? 2, right? TF is equal to 2.
Is 1 over n given, or do we have to like figure that out somewhere?
The fact that TF is 1 over n?
Yeah.
It's, well, we did that up here. We said that TF is 1 over n, where n is equal to n2 over n1. And so
So I was just given that.
it's gonna, when you come to a specific problem, you have to interpret which of your sides of the transformer is n1, which of them is n2. So once you define that, then you have transformer ratio defined for you. Because it's a transformer, it's always 1 over n, which is equal to n2 over n1. So, yeah. Okay, so we have that defined. Let's do our elemental equations. So that was a little sidebar that'll help us with our elemental equations. But let's do all of our elemental equations. We need to write one for every passive element in the entire graph, right? So that's 1, 2, 3, and then this transformer is going to have 2, right? So we're going to have 5 total. So let's do the easy ones first. R1 is equal to R1 IR1, right? And VR2 is equal to R2 IR2. I guess I should have written the column, right? I've always been doing that. I should do that. So this is our R1 equation. This is our R2 equation. C, and then there are these 2, so we could do like 1, 2, just to show that for the transformer we've got 2 there. Our capacitor elemental equation is dVc dt equals 1 over C IC. And finally, we have, since it's a transformer, it always has this. It's an electrical transformer, or it's any transformer. It always has this as its 2 elemental equations, with whichever cross variable in there as appropriate. In this case, it's voltage and current, right? So we have voltage 1 and current 1 equals TF 0, 0, negative 1 over TF times V2 I2, right? I just transcribed that from up here. Now, we want to make sure that all of these are written with the primary variable on the left-hand side, right? So let's do that. So our VR1 is not a primary variable, so we have to solve that for IR1, don't we? So IR1 equals VR1 over R1. VR2 is a primary variable, so we're good on that. So VR2 shows up there. VC is a primary variable. It happens to be our state variable, so it's on the left-hand side already. So that one's good. Now, what we have here, we have V1 and I1 on the left-hand side. Now, V1 is a state variable. I1 is not, or sorry, is a primary variable, and I1 is not a primary variable. So are we totally screwed?
No, you can write those as individual
Yeah.
equations.
Let's just write them as scalar equations. There's no reason not to. I don't know where this came from.
I can't delete it.
I can't do that on mine.
I'm gonna just do that.
You can't do it.
Oh, you guys can't do that?
No, it's paper.
Oh.
That's where we're going anyway.
So what you guys are saying is lesson learned, huh, for you guys? Yeah. Alright. So let's rewrite that as 2 scalar equations. V1 equals what?
TF times V2.
Yeah, TF times V2 and plus 0 times I2. Right? So we'll just leave it like that. Somebody like hosting a dinner party next door or something? So then I1 is equal to 0 times V2 plus negative 1 over TF times I2. Negative 1 over TF. And to absolve ourselves of any ambiguous notation, we'll put parentheses around it. So we have two equations. So now we need to make sure that the primary variable is on the left-hand side. V1 is a primary variable. I1 is not. So we need to solve for I2, which is a primary variable. So that gives us I2 equals negative TF times I1. Dum, dum, dum. All right, is that what I deleted?
Yes.
It's bad.
That's funny. My notes are all messed up, and I don't know why. So I'm doing this live in front of you, so hopefully we get to the right answer. I feel pretty confident, though. I feel it's only first order, guys. We can do it. We can do it. Plus, we're really smart. So there's that too. I'm really smart. I'm just kidding. Just kidding.
I can only speak for myself.
Yeah. Well, so I filled in this stuff, huh?
Yep.
But we'll talk about this. Talk about this. All right. I have like random stuff filled in and not on this one, so I think that. Well, that's my bad. That's my bad. So continuity equations are next up, right? So we'd use the same exact process to find the continuity equations. Nothing is new here. So we have to intersect. So I redrew our linear graph here in our normal tree. We have to intersect the normal tree once with each of our contours, and we have to intersect only the a single passive element in the normal tree. So we have that here. There is a single intersection. There's another one with a single intersection, and there's a final one with a single intersection. So those are all valid. And so we can go ahead and write them. So this one says that I1 is equal to IR1. Right? Now, we could have written IR1 minus I1 equals 0, and then solved for I1, right? And found out that it's equal to IR1. Either one is fine. I recommend always starting with the whatever element you're intersecting in the normal tree, writing that through variable equals whatever goes in. That's my recommendation. So IR2 is the next one that we do. IR2 is equal to negative I2, right? Because I2 is leaving. And then finally, IC is equal to negative I2. Why is it equal to negative I2?
He's going in and I2 is going in.
Yeah, exactly. So they have to have opposite signs. Otherwise, something's accumulating there at that node, but we don't allow for that. That can't be the case. My friend, we're really nerdy. You guys knew that already. Okay, so my friend sent me a message this morning, so I kind of like woke up groggily as I was like walking to the bathroom. I was reading this, and he said he wrote You guys heard of the Fibonacci series? Fibonacci series. I laughed at that. I thought that was pretty funny. Fibonacci series 999. You guys know that clip with Hitler? So 9 means no in German, and so it's less funny when you explain it.
I get it. He's funny.
Yeah, pretty good. Pretty good. Okay, so
Sounds like the doctor of Deep. She loves bad math jokes.
Bad math jokes. Yeah, I should send it to her. I often bad math jokes, like, I don't know. Sometimes I'm like, yeah, okay, that wasn't very good for me. But that one got me. I was like, yeah, that's a good one. It's because it took me a second. I was like, I think I read it Fibonacci series, and I was like, 9. This is just 9s. Like, he like wrote a lot of 9s, and I was like, it's like, no, these are all 9s. I'm like, what is? I'm really confused. And I went back and looked at it, and it was Fibonacci. And I was like, got it. Got it. So, I don't know where he came. Well, he said his wife told him, so I don't know where she came up with that. She might have just made that up.
Probably a Facebook name.
Could be. We'll say she invented it, though.
Yeah.
Amanda Powell. She's now on the internet forever. Assuming I don't take these videos down, which I probably will.
Sounds good.
Okay. Compatibility equations are next up, right? How many are we going to have? You have them on your page, doesn't matter. Okay. So we have 2, right? 1 for each of these twigs, the elements that are not in, you guys laugh at that, elements not in the normal tree. So we got to write one for this and write one for this. So the first one we'll do is this. So VR1 has to be equal to VS minus V1, right? And that is what I wrote there. V2 is this one. It has to be equal to VR2 plus VC, right? And they're already solved for the secondary variables if we write them like that, in that method. So that's what I like to do. We're going to come back to this aside in just a moment, okay? We're going to go through... Oh, I gave you guys this part. Well, let's walk through it.
I finished.
Done. All right. So the algebra part is, the usual thing. I usually can see where it's going, and I like to list the state equation ones that have the state variable derivatives on the left-hand side first. Yeah.
Just regarding the way we draw transformers in the linear graph, is it convention to make sure that their arrows and the branches are supposed to be pointing the same way?
Yes.
Okay, just want to be
Yes.
sure.
And yes is the short answer to that.
Okay.
Yeah. Otherwise, you have to change signs in your transformer equation.
Okay.
And I don't recommend going that route. You can do it, totally legal.
Only if you
Ill-advised. If you get the sign right after you go that route, then that's really good. It's really hard to get the sign
get a
right.
special achievement.
Yes. Unlocked. So, we're being super nerdy today.
This Friday.
Yeah, that's good. And I'm wearing casual clothes. We're going to get through this example, though. And this aside. Okay, so dv dt is equal to 1 over c times IC, right? But IC has, of course, a continuity equation. Plug in negative I2, so bam, I already did that. IR1, you can plug in VR1 from this compatibility equation. There you go. And VR2 is equal to R2 times IR2, and there is a continuity equation for IR2 equals negative I2, so we plug that in. V1 from up here is equal to TF V2. So V1 is equal to TF V2. V2 is VR2 plus VC, right? So bam, did that. I2 is TF, negative TF times I1. I1 is equal to IR1, and so we can plug in IR1 there. So we just used all of our continuity and compatibility equations. We just burned them off. Okay, and now we're left with 5 1, 2, 3, 4, 5 equations that we need to get down to how many? 1. So we've got to do some elimination. And now is the part where I tell you that sometimes the algebra, when you have a transducer element, sometimes the algebra is harder. Okay? It sucks, but it sometimes can be harder. So I'll walk you through the algebra here, and we'll start here. So dV/dt is equal to negative 1 over c times I2. We plug in I2 from down here, right? So I check that. So the negative sign became positive. What's going on out there? Anyways, and then IR1 there's an equation for that from the other elemental equations. We plug that in. And then so Vs is a source variable, so that one's good. But V1, we got to get rid of V1. There's going to be an elemental equation for that, so plug that in. We get to here. Vc is a state variable, but VR2 is not. So VR2, plug that in, and we get this. Great. I2, so everything's good except for I2. We can plug in this state equation, this one, there, and we get IR1 again. And at this point, almost every one of you at some point will start to go in circles. Okay? But I want to draw your attention to the fact that we have now burned through all of our equations, and we didn't get to what we were hoping for, which was getting rid of all of our non-state, non-input variables. And this is where there's a little bit of a trick that comes in. Once you burn through that last one, you have the opportunity. So I2 is equal to negative TF IR1, and you burn it. But notice that IR1 from this initial equation is equal to something with dV/dt in it, and you can plug that in and have dV/dt on both sides of the equation. Okay. Woof. Right? Recognizing that is hard.
There's like some integral trick like that too.
Yeah, I don't have a good answer for this. I don't have something that can say like every time you do this is going to be. You have to recognize though, and it happens with transducer. When you have a transducer in there, the algebra can get like this. And it's just how it is, and there's no like. If we used linear algebra techniques to do the algebra, we wouldn't need to worry about this special case because you can solve it in general. But I don't teach that method. I just think it's a little bit more advanced in linear algebra than we need in this class. So you need a little bit of insight to see that you can do this loop, and that then you can have dV/dt on both sides of the equation. You have to move them to the same side, factor it out, and then divide everything else over. And you end up with this mess for dV/dt.
Wait, what happened to the other?
So it's another thing that you guys can't do. It's just that it gets a little bit messy, okay? And I don't want you to be intimidated by it. So I want you to go through this, see if you can see the trick, see if you can figure this out, and then you'll have homework on it. But before I let you go, I have to talk about transformers versus voltage dividers, okay? So output voltage for a transformer can either go up or down, right? So you can either increase voltage or decrease voltage. Voltage divider, the output voltage can only what?
Go down.
Yeah, it can only decrease. The frequency row here is there because a transformer only works for AC signals And one downside of it with frequency is that in frequency, sometimes they can be non-linear. Not in the models that we've developed here, but in some models they can be non-linear. Whereas voltage dividers work for DC or AC, and they're very linear. Okay? So that's one thing. So if you want to drop down in voltage, there's some trade-offs there. For power, for a transformer, power is roughly conserved. Okay? But for a voltage divider, there are much more significant losses for power. And then finally, with bulk, a transformer tends to be much, much larger than a voltage divider, which just requires a resistor. So those are the sort of the design trade-offs that you have in that case. Okay, thank you guys. Have a good weekend. Thanks.
That